multivariable optimization with no constraints or without constraints. The necessary condition, let x equal to x1, x2, etc. xn. If f of x has an extremum point or maximum or minimum at x equal to x star, and if the first partial derivatives of f of x exist at x star, then their first order partial derivatives are all equal to 0. That is dou f by dou x1 x star equal to dou f by dou x2 at x star etc. equal to dou f by dou xn at x star equal to 0. Now we can see the definition of positive definite, negative definite and positive semi-definite. We know that a matrix A will be positive definite if all its eigenvalues are positive. We can use another test to find the positive definiteness of a matrix A of order n, which involves evaluation of determinants. Here capital A1, capital A2, etc. capital N denote the principal minors of a matrix A. That is A1 equal to A11, A2 equal to A11, A12, A21, A22, etc. The matrix A will be positive definite if and only if all the values A1, A2, etc. An are positive. The matrix A will be negative definite if and only if the sign of Aj is -1 down raised to j for j equal to 1, 2, etc. n. If sum of Aj are positive and the remaining Aj are 0, the matrix A will be positive semi-definite. Now we can see the definition of Hessian matrix. Let f of x be a scalar valued differentiable function for x equal to column matrix x1, x2, etc. xn. Then the Hessian matrix J of f of x is defined as J equal to matrix consisting of all second order partial derivatives. In particular, when x equal to column matrix x1, x2, Hessian matrix J equal to matrix consisting of dou square f by dou x1 square, dou square f by dou x1, dou x2, dou square f by dou x2, dou x1 and dou square f by dou x2 square. Necessary and sufficient condition for optimization of multivariable objective function without constraint. We can see the working rule. Find the maximum or minimum of the function f of x where x equal to the column matrix x1, x2, etc. xn. In first step, we had to find the necessary condition. The necessary condition for a function f of x with continuous first and second partial derivatives to an extremum point at x star is that each partial derivative at x star will vanish. That is dou f by dou x1 at x star equal to dou f by dou x2 at x star, etc. equal to dou f by dou xn at x star equal to 0. In step 2, by solving the above equation, we will get the stationary points. These points include inflection saddle points. Therefore, the given conditions are necessary but not sufficient for determining the extreme points. So, to find the nature of stationary points, we have to use sufficient conditions in step 3. A sufficient condition for a stationary point x star to be an extreme point is that the matrix of second partial derivatives, that is Hessian matrix of f of x, evaluated at x star is positive definite when x star is relative minimum point and negative definite when x star is a relative maximum point. In step 4, we will calculate the optimum or extreme value of f of x. After finding the nature of stationary points obtained in step 2 using step 3, find the extreme values of given f of x and the corresponding extreme points x star if necessary. Now we will see the definition of saddle point. In the case of a function of two variables f of x, y, the Hessian matrix may be neither positive definite nor negative definite at a point x star, y star, at which first order partial derivatives are equal to 0. In such a case, the point x star, y star is called a saddle point. from the figure, we can see the saddle point. Now we can see an example. Find the extreme points of the function f of x1 x2 equal to x1 cube plus x2 cube plus 2x1 square plus 4x2 square plus 6. For finding the solution, first of all, we will find the necessary conditions for the existence of the extreme point. That is, first calculate first order partial derivatives dou f by dou x1 and dou f by dou x2. Then equate to 0. We will get the extreme points. The points are 0, 0, 0, minus 8 by 3, minus 4 by 3, 0, and minus 4 by 3, minus 8 by 3. To find the nature of these extreme points, we have to use the sufficiency conditions. For that, calculate the second order partial derivatives. That is, dou square f by dou x1 square equal to 6x1 plus 4. Dou square f by dou x2 square equal to 6x2 plus 8, and dou square f by dou x1 dou x2 equal to 0. Now find the Hessian matrix J and find the principal minus of this matrix, let it be J1 and J2. From the table, first column corresponds to the points, extreme points. Second column corresponds to the values of J1. Third column corresponds to the values of J2. And fourth one gives the nature of the Hessian matrix. And the fifth column gives the nature of the point. And last column gives the value of the function. Multivariable optimization with equality constraints. In this section, we will see an optimization problem with equality constraint. Let it be minimize f equal to f of x subject to gj of x equal to 0 or j equal to 1, 2, 3, etc. m, and x equal to the column matrix x1, x2, etc. xn.